Assuming you've completed the film calibration step, I'm going to show how to calculate a dose map using the EBT3 Rapid Arc example included in the Film QA Pro installation package. The route is shown on the screen. With the calibration object in place and completed, the next step is to add a dose map object. So click on the line Add New Case Object under Case Object Management at the bottom of the case tree. Pull out the menu and select Dose Map Single Scan. After the Dose Map Single Scan object appears in the case tree, click the plus sign to expand the dose map object. To introduce a dose map film, right-click on the first line of the object. There are two ways to add a film image. Either scan a film to obtain the desired image, or, as in this case, to load the image from file. To start, I'll demonstrate generation of a regular dose map, but I'm also going to show how to calculate a dose map using the reference strips in the image you've just loaded, together with the one-scan dosimetry protocol. So navigate to the example EBT3 Rapid Arc folder and load the file dosefilm0_313.tif. The 0 and 313 embedded in the file name are the dose values in centigrade for the reference film, and you'll need them later. The principles behind the one-scan protocol are contained in the medical physics article referenced on the slide. Since the case already contains a calibration, as soon as the dose film image is loaded, calculations begin using the triple channel method. The theory and mathematics behind multi-channel radiochromic film dosimetry has been published in Medical Physics as referenced on the slide. Since most images have at least hundreds of thousands of pixels, there are a lot of optimization problems to solve in completing the multi-channel dosimetry calculations. Depending on your computer system, this may take anywhere from a few seconds to a half a minute, during which time the little star in the lower right-hand corner of the screen will turn blue to indicate the process is underway. And if a case tree has multiple dose map objects, there could be multiple calculation tasks in process, as indicated by the numeral next to the star. When the calculations are done, the dose map appears as a thumbnail on the branch just below the dose film. And below that, there is a thumbnail image showing a consistency map. This map shows the correspondence of the calculated dose values in the three color channels. Essentially, it is a map of dose uncertainty, and ideally, all three dose values should be the same. For now, click on the thumbnail image of the dose map. We'll return to the consistency map later. The dose map should now show in the image window. Let's begin by looking at the dose values of the reference films. They should be 0 and 313 centigrade. To do that, click on the frame selection tool. It's the icon at the top of the toolbar in the image window, and draw region of interest frames in the center of the reference films. Then click the Statistics tab. It's the third tab down in the Analysis window, and a table of dose values appears. The first two columns of the table show values near the cursor and in the whole image, but ignore them for a moment and look at the values in frames 1 and 2. Values for frame 1 are close to 0 in each color channel, and for frame 2, the values should be close to 310 centigrade. The differences between measured and expected values are the result of scan-to-scan variability, perhaps due to the scanner itself, or perhaps due to temperature differences between the time the calibration films were scanned and the time the dose films and reference films were scanned. But if you stop right here, you've accepted a 1% offset in your dose map. So let's see what can be done to eliminate it. This is where the one-scan protocol can be applied. As I mentioned before, the principles have been published in Medical Physics. We'll begin by right-clicking on one of the regions of interest on the reference films and designating that ROI as a calibration region. Notice that the frame changes color as I do that to indicate it's now a calibration region. Right-click again on the frame and choose Calibration Value from the menu. The first calibration region is on the unexposed film, so the dose is 0. Type in the 0 value when the calibration value panel appears, and then hit Enter and OK to accept the value. Now repeat the process for the exposed reference strip and the reference dose of 313 centigrade, making sure that the dose value has the right units. Now right-click on the top line of the dose map object, just where it says Dose Map Single Scan. And from the context menu, select Dose Mapping Method, then Recalibration using Reference Regions, and Dose Linear Scaling. Return to right-click once more on the top line of the dose map object and select Rebuild Dose Map. Again, the blue star in the lower right corner of the analysis window shows that the calculation task is in progress. Calculations might take from a few seconds to half a minute, depending on the image size and the computer hardware. And upon completion, the thumbnail images of the dose and consistency maps are refreshed. Click the dose map thumbnail to display it in the image window, and then click the Statistics tab to look at the dose values in the reference films. The exposed film is now exactly 313 centigrade in each color channel. For the unexposed film, the displayed values are not quite 0, but this is only because FilmQA Pro doesn't recognize negative dose values, and any negative value from the calculation is set to 0, but statistically, the values are correct. The dose map is ready to use. Right-click the thumbnail to save it as an image, or use the image export icon on the toolbar to export a table of comma-separated values to another application. Any film or dose map image can be saved or exported as a 3-channel image, or files can be created from any of the channels individually. With the dose map calculation complete, let's take a quick look at one of the useful data displays. A dose profile across any selected path on the dose map can be displayed in the analysis window. Do this by using the Profile tab in the analysis window and clicking the Profile tool icon on the toolbar along the left edge of the image window. You can select from vertical, horizontal, diagonal, circular profiles, etc., and then use the mouse and cursor to specify the path to be profiled. After drawing the profile line, click again on the profile icon or on the line to select the width over which averaging occurs. Alternatively, the profile line can be manipulated using the buttons at the bottom of the analysis window to control XY position, length, width, and orientation. Turn a button with the cursor, or click on a button and move it with the mouse wheel or the arrow keys on the keyboard. Finally, use the colored spherical icon on the lower right of the analysis window to show a chart with dose profiles for any combination of color channels. Let's return to the consistency map and explain its value. Click the thumbnail image to display it in the image window and draw a profile across the middle. The consistency map represents the uncertainty in dose measurement. For each pixel, there are 3 measurements, 1 dose for each color channel. Consistency is defined as the average dose difference between each of the pairs of channels, red-green, red-blue, and green-blue. It can be displayed as either the arithmetic or geometric mean, or as the maximum difference between any of the 2 channels. The ideal consistency value is 0, which is to say that the same dose is measured in each color channel, in which case the map in the image window would be black. Plot a profile across the consistency map. In a good dose map, most pixels will have dose consistency values about 1%. These are values expressed as the arithmetic dose average divided by absolute dose. In the example, most doses in the profile are between 1 and 2.5 gray. So with absolute consistency values in the 1 to 2.5 centigrade range, this is a good dose map. However, if consistency values are mostly greater than 3%, it indicates a possible mistake somewhere in the measurements, such as the film was not oriented or placed on the scanner correctly. The calibration used was for a different film lot, or was obtained on a different scanner. The map is scaled so the largest consistency value is displayed as white, and this usually corresponds to any marks written on the film, for example, fiducial marks, ID numbers, or often the very edges of the film itself. In these areas, the measured response values have no correspondence to film calibration, so the dose values and the color channels are very different. Therefore, it's not always a good sign to have a very dark consistency map, which may have resulted from the wide image scaling range. To better explore the consistency map, start by using the frame selector tool on the image window toolbar to mark a small region of interest. Then use the color spreader tool on the toolbar to stretch the values in the region of interest to the maximum and apply the settings to the displayed image. But in this case, the consistency values are generally 1% or better, indicating that these are reliable dose measurements. In this tutorial, we have created a dose map using the triple channel dosimetry method, but you can also calculate a dose map using single channel or dual channel dosimetry. Right-click the top line of the dose map object and select Dose Mapping Method, and choose from Dose Map from Single Channel Calibration or Dose Map using Density Reference Channel. Each of these selections results in the calculation of 3 maps: red, green, and blue channel maps from single channel calibration, and red-blue, red-green, and blue-green maps with the density reference method. The red-blue dose map is essentially the same as the proposal we made several years ago to do dosimetry using the ratio of red and blue responses, wherein the response of the blue color channel provides a correction for small non-uniformities in the film, as well as for certain scanner artifacts. Another feature available on the dose mapping method provides the ability to recalculate a dose image with a different scaling range. By default, dose maps and consistency maps are automatically scaled between 0 and a value somewhat greater than the highest value in the image. Remember, negative dose values are always reset to 0. Automatic scaling is usually satisfactory, but sometimes, because of marks scribed on the film in black ink, or the use of an opaque mask to help position the film on the scanner, the highest calculated dose values do not come from dose to the film. If this is the case, the dose resolution and dose precision may be diminished, and it may help to scale the dose map manually. Click the Info tab in the Analysis window to display the scaling of any dose map or film image. If the dose map scaling range differs greatly from what you expect to have been recorded, consider returning to the dose mapping method in the dose map object and select User-Defined Dose Range to set the dose range manually. Remember to type in the dose value and check the dose units before hitting the Enter key and then OK. As soon as the new dose range is entered, the dose map calculation refreshes. To illustrate the difference, this slide shows dose maps with ranges of 0 to 350 and 0 to 1000 centigrade. Not only does the higher dose range diminish the brightness and contrast of the display, but it also reduces the precision and dose resolution. But remember, too low a dose range is also not good, since it truncates any calculated doses higher than the chosen maximum. That is, these higher values are reset to the maximum value of the dose range. That finishes the dose map tutorial. The next module explains dose-to-plan comparison, where the dose map and treatment plan are overlaid and analyzed.